Hello, fellow pedestrians. In our last video, we talked about how certain symmetries, when present, are able to reduce the order of a second-order differential equation to first. From now on, though, we will only concern ourselves with linear differential equations explicitly. So, to begin with, let us make an observation that can be applied to all homogeneous second-order Ds, the linear that is. So assume that you have a second-order linear differential equation written in this way, and it is apparent that you have a scaling symmetry of y, and this is always the case, right? Now, trying to solve linear equations using special scaling symmetries is very ill advised, to say at least. Sometimes try to solving one of the above fashion and utilize the inherited symmetries to reduce their order at the expense of their linearity should only be confronted as theoretical possibility without any practical value at all. To even concern ourselves something like that, so imagine using scaling symmetries or whatever symmetry to solve, like we said, the constant coefficients, which is of this form, is nonsensical at all. Or try to solve an Euler equation, that is, which has a very trivial solution. Now, doing this is at the expense of the linearity. So what you are up against is, yes, indeed, a lower order the differential equation, but a very complex one that is. Meaning that yes, you do have a nonlinear differential equation of first order, but most of the time it's going to be much more difficult to oppose. So I would personally only concern the shifting symmetry when possible. So if you have for linear differential equations, the only symmetry that I personally would recommend using is only the most trivial one, which is the shift of y. So in the case where this term is missing, right? It's the only case that we can apply this transformation. Every other transformation made into a linear equation, doesn't matter which, would only make it more difficult most of the time. So uh, from here on, we will only concern ourselves only with linear differential equations, like we said. And to do this, we need to establish some technicalities that are essential for our upcoming tackling of the linear differential equations. So, we're going to start. Let's erase everything with singular points. It would take a while to see why we're going to do all this work, but it will pay off. Now, let a second order ODE to be of the form y prime prime plus p of x, y prime plus p of x, y is equal to 0. Now, firstly, we define if p of x and p of x are finite at x equals x naught, then x naught is called an ordinary point, and everything is fine. Now, if either p of x or q of x diverge as x goes to x naught, then the x naught is called a singular point. It is a singular point. And this can be subcategorized twice, meaning that if x minus x naught times p of x and x minus x naught squared times q of x are finite as x goes to x naught, then x naught is a regular singular point. Otherwise, it is an irregular singular point, or just a singularity in some bibliographies. Singularity. And we're going to check what that is. Now, this is the way that we can check for points if they are ordinary, singular, regular, or irregular singular for a differential equation. Now, when this point is at x naught, but what happens at infinity? So, to check for singularity at infinity, is possible by transforming x to 1 over z. So when this goes to infinity, z is going to go to 0, and we define the following functions to z minus p of z minus 1 over z squared if it diverges faster than 1 over z, and the second one is q of z minus 1 over z to the fourth if it diverges faster than 1 over z squared. If either of these two is true, then infinity is an irregular singular point. Otherwise, it is not. Okay. Now, there is a point for doing all of this, and we'll get to it. Now, let's check some examples and check if there is a singularity of or a regular point, etc. Now, let's check an equation that is called the Bessel's equation, which is x squared y prime prime plus x y prime plus x squared minus n squared y equal to 0, where this is just a constant. Now, if you write it into the canonical form, which is this form here, this can be written as y prime prime plus 1 of x y prime plus 1 minus n squared over x squared y is equal to 0. Now, to check if there is an abnormality or a singular point at 0, because this is what we usually check, we usually want power series to be expanded around 0, but of course this is not binding. So, to check what happens at 0, because you can see that p of x and q of x has poles for x at 0. So as x goes to 0, so they're certainly not they're not ordinary points. So x times px goes to 1, right? So regarding this, which is finite, this is fine. This is just a singular point, and not an irregular one. And x squared times q of x is equal to x squared minus n squared. So when this goes to 0, this just goes to minus n squared, which is also finite. This is just a constant, a finite constant. Meaning that x naught equals to 0 is a regular singularity. So we checked the obvious pole, the obvious point where Bessel's equation could have a regular or irregular singularity. But what happens as x goes to infinity? So for x goes to infinity, we have 2z minus p of z minus 1. So this is just z, because the reciprocal of this, over z squared, which is nothing more than 1 over z, right? So it doesn't diverge faster than what we got. And we're going to do the same for this guy here. So q of z of minus 1, which is going to be written as 1 minus n squared z squared over z to the fourth, right? Which is nothing more than 1 over z squared minus n squared over z squared. But this term diverges much faster than z squared, which we set as our limit, meaning that this diverges faster, so this is an irregular singularity, meaning that Bessel equation has an irregular singularity at infinity only. Now another example. Let's check the infamous Legendre equation. 1 minus x squared y prime prime minus 2xy prime plus L times L plus 1y is equal to 0. Now, if we bring it to the form we want, which is minus 2x over 1 minus x, you can write it this way to immediately check for divergences for poles. So plus, there is a y prime here, plus L times L plus 1 over the same y is equal to 0. So this is p of x and this is q of x again. Now let's check for the case where x goes to 1. Now as x goes to 1, we have x minus 1, because 1 is going to be the x naught here, times minus 2x over 1 minus x 1 plus x is going to be 2x over x plus 1. And for x going to 1, this is just 1. Now, we're not going to do the same for minus 1. You also get a finite number. So, doing the same for q, x minus 1 squared of L plus 1 over 1 minus x 1 plus x, this and this cancels. What we left with is L plus 1 over uh, 1 plus x. So, which is just 0. So again finite. So x not at 1 is a regular singularity. The same way you can show that x goes to minus 1 is also a regular singularity. Now what happens as x goes to infinity? We will have 2 of z minus, now we have, now this is uh, our p of x, so it will be written as minus 2 over z, 1 minus 1 over z squared over z squared, right? And this is nothing more than 2z plus 2z over z squared minus 1 over z squared and 2 over z plus 1 over z squared, right? So it is indeed an irregular singularity at infinity. Again, for the Legendre function. Here, right? We're only keeping the relevant terms. Now, let y be a power series. That is a solution to a second order ODE. We'll have 3 points. Just some theory that we are going to utilize a lot lately. Now, if there isn't any singular points, then y of x will converge everywhere. So from minus infinity to infinity. Now, if the series solution is expanded around a point, say x naught, which is not an ordinary point, then the series will converge at least at the interval x naught minus r, comma x naught plus r, where r is the distance of x naught to the nearest singular point at the complex plane. R is also called radius of convergence, and we'll see soon why. And finally, if we expand around, x naught, which it is now a regular singularity, then the series will converge at almost the same interval, but without the point itself. So, comma 0 and h0 plus r. And we never expand around points at irregular singularities. Later on, we can check what happens specifically at this point, depending on the positiveness of the root of something called the DCL equation, and we'll see how and the way it will work. There is an exception to all of these. The exception has to do when the series we're talking about is going to break down to a polynomial. And naturally, this won't hold. Now, let's do something more fun to close this lecture. Let's check the convergence of power series. Say an xn. Now, the most famous test there is to check for this, there are many tests of de L'Hopital, of Cauchy, of Gauss. The most famous that is widely used is something called the ratio test. And this is how it works. Let's define a term called L, which is equal to the limit when n goes to infinity of a term n plus 1 divided by its previous term. For this to converge, imagine that you have a series and the fraction of the last, let's say, term over its previous, for the series to converge, this has to be less than 1 for convergence. So this is the test we're going to apply. Now, how this uh, can be how this is relevant with everything we talked so far. It is. The radius of convergence which we said we denote as R is written as the reciprocal of L. And this can take three values. It can be, if L is 0, that means that R goes to infinity, meaning that the series converges everywhere. Why? Because the radius of convergence is limitless. Now, if L is infinite, then the radius of convergence is 0, meaning that the series converges nowhere except at x0 itself, the point we are expanding around, right? And finally, if L is finite and different than 0, then we're going to find R as 1 over L. Now, from practicality only, in general, the most straightforward way to find what the radius of convergence of a power series is the following. When you're going to do the calculation, and we'll see exactly how, you're going to stumble across a point where you will have the limit of n goes to infinity of some term, let's say x minus x naught, if it's expanded around x naught, over some constant to the j, where j is just a number, and you're going to need this to be less than 1 for convergence, then this constant is nothing more than r itself. And let's get to example. Now, we'll see one of its examples to make a point. Imagine we have the power series and from 0 going to infinity, minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Okay, now if we take the limit when n goes to infinity of this term over this term, what we are going to have is absolute value of minus 1 to n plus 1 of x to n plus 3, we send n to n plus 1, over 2n plus 3 factorial, minus 1 to the n, x to the 2n plus 1, over 2n plus 1 factorial, right? And this is nothing more than lim when n goes to infinity. We'll have minus 1 here, but this is an absolute value, so I'm not going to even write it. So x squared at the denominator, because there's 3 and 1, and the denominator, sorry, and at the denominator we're going to have 2n plus 2 and 2n plus 3. Now, as n goes to infinity, this goes to 0, right? What does it mean? It means that this power series is going to converge everywhere. So we do not expect this power series to have any singularities or anything. It's going to run perfectly at its points, right? And this power series is nothing more than the expansion of sine of x. This is how sine of x is written as a power series. So it makes totally sense that it converges everywhere. There's no singularity or anything. It works totally fine for all of R. Now, so this was this case. Oh, sorry, this case, right, where it converts everywhere. Now let's take a case where we do get a finite number. Say we have the power series from 0 to infinity of x squared over 4. This is 4, supposedly, to the n. Now this is called geometric series, and its limit convergence is given as 1 x squared over 4 for r absolute less than 1. Sorry, less than 2. This is given, but we're going to prove it. So the limit when n goes to infinity of x to the 2n plus 2 over x to the 2n, and this is going to be upside down, so 4 to the n, 4 to the n plus 1. Now, this is nothing more than this goes away totally with this, so 1/4, and this leaves just x squared. But, like we said, we got something like this. So this can be written as x over 2 squared, this is equals, right? and we demand this to be less than 1. But you can totally see what the radius of convergence is. It's 2, meaning that R is 2. So this series will converge only at minus 2, from minus 2 to 2, since there are no other singularities in between these rates. Now you see, like we said, r is the distance from the center, right? Which is 0 in this case, because this is expanded around 0, to the closest singularity, which is indeed at 2. The thing is, while this function is well defined for x bigger than 2, it diverges when written as a power series. This is because the power series itself only encodes information inside its radius of convergence. So for x less than 2, inside this disk, the series behaves like a well-behaved polynomial approximation, let's say, right? Now, to convince ourselves that what happens outside of this range that we found, and we say that the power series will divert and will converge inside of this. Now, to check this and be convinced, let's check our uh, code editor and see what happens. So what we had was x squared of 2 over 4 and all to the end. Oops. And I have this ready to sum up all terms, and this is the number of terms we are going to sum. We can choose to sum one term or 10 terms, it doesn't matter, but for a better approximation, the more terms the better. So let's see what happens at 0. At 0, what we're going to get is 1, okay? Nothing strange. What happens at 1 when x is equal to 1? It's 1.333333. You can easily check that this will coincide with the approximation, actually the actual limit, which was 1, I think 1 over 1 minus x squared or something. Yes, x squared over 4, right? Now, if you set x to 1, the denominator will give you 1 minus 1/4, so the denominator is 3/4, and the whole fraction is going to be 4 over 3, right? So at x equals to 1, this gives you 4 over 3, which is nothing more of 1.333333. The result we got for x is equal to 1. So this is indeed a very sustainable approximation, a very sustainable limit. Now, what happens at 1.9, near the limit, near the radius of convergence? Everything's fine. You get 10. What happens at 2? So let's kick it up a notch. At 2, it goes to 1,000. Why? Because we have 1,000 times of 1. Right. Now, if you go to 2.1, where we insist that the series will diverge, well, this is pretty much infinite with respect to this, going from such a small differential from 1,000 to some billions of billions of billions of billions is crazy. And imagine going and set this to 10. I mean, you get a number which has 1396 zeros. That's a lot of zeros, right? And of course, for minus 10, the same goes for the other end of the range. We still get infinity, or pretty close to it. So this is pretty much it. Now that we convinced ourselves that it does indeed converge for the range of between minus 2 and 2, and it diverges outside of this range, now let us check a last example, namely 0 to infinity of n factorial x to the n. Now the limit of n goes to infinity is going to be n plus n factorial over n factorial, and x to n minus plus 1 over x to the n, right? And this will simplify to just n plus 1. But since it goes to infinity, 1 is very small compared, so just n. And this is just x. And when n goes to infinity, this still goes to infinity, meaning that the radius is 0. Hence the series should only converge nowhere except x naught is equal to 0. And if you expand this is nothing more than 1 plus x plus 2 x squared plus so on and so forth. So at 0 you'll get 1. And of course you can also check this. This is a factorial x to the n. This is much more trivial to check, but why not? So factorial n times x to the n. Now we said for any value of x going to diverge. Well, this is a pretty big number, right? This is, we have three, what is it? It's 3,563 zeros that are multiplied with minus 4, right? What happens at 1? At 1, it's pretty close to infinity as well. And at 0, we should expect to get 1, the only point that the series does converge. And this is true as well. So, this was pretty much it for the time being. Talking about singularities, talking about singular points on power series and when they converge. And thank you all, and I will see you on the next video. Thank you.